Hello everyone. Welcome to the next part of the unit. To begin with, we will start with basics of oscillator. Now the first concept under this is stability of feedback amplifier. We already seen the graph about the frequency response curve, wherein in feedback amplifiers we have seen that gain versus frequency curve provides me about the mid frequency, about the lower frequency and the upper cutoff frequencies also. Okay. Now with respect to stability, we know that gain, that is A, and phase shift, okay, these both are frequency dependent. Okay, because we have seen over here, you can see that gain at lower frequencies, what happens over here, it is less. At higher frequencies also it is less, it decreases basically. So similarly you have phase shift also, which changes with frequency. Now when I say phase shift changes with frequency, it introduces a positive feedback in amplifiers. Okay, so at higher frequencies it adds some feedback to the input signal, so it results in positive feedback. Okay, so when I say positive feedback, definitely amplifier will give out oscillations. But that amplifier is not good, which will simply produce oscillations at any point of time. Okay, it is basically a disadvantage that your amplifier is not behaving the same at all frequencies. Fine. So what we need to do is we need to design the circuit in such a way that it remains stable for all the frequencies. Okay, so for a system to be stable, all the poles and zeros of the transfer function must lie on the left half of the complex plane. Now what do you mean by this? First of all, we'll understand what is a complex plane. Okay, I have sigma plus j omega over here. So here's the real axis, here's the imaginary axis. So this is my complex plane altogether. Now in this particular complex plane, I have the left side and the right side. Now if at all poles and zeros lies on the left side, that time I can say that the system is stable. Okay. Now what is a transfer function? Transfer function is nothing but output upon your input. Okay, any system will have output and its input. So when I do output upon input, I get the transfer function. Poles and zeros can be given by this particular equation over here. You all can see this is my transfer function h of s. Okay, it has its numerator and denominator. Now to recollect, you all in ECS you all must have studied about positive real functions. Okay, even with respect to Foster form, Cow form, you all remember we used to write the terms over the s plus 3, s plus 2. Okay, and then you have a s square plus 2s plus 1. Such terms existed. Okay, what does that s denote? It denotes that you have to use a Laplace transform. Okay, basically analog domain. Okay, so similarly you have an equation which is put up over here, s minus z1, s minus z2 till s minus zm divided by s minus p1 till s minus pn. Z denotes zeros, p denotes poles. Okay, now if at all these poles and zeros they lie at the left half of the complex plane, that time I can say that the system is stable. And we can see over here there are some poles which are denoted by x and zeros by 0. Okay, if at all they are at the left side, they are stable. Right side, they are unstable. And if at all on the axis they lie, it is marginally stable. Okay, brief idea about poles and zeros which you will be studying in detail in SAS. Next is the Nyquist criterion, another important parameter to decide on the stability of the network or the amplifier. It decides on the stability depending upon the Nyquist diagram. Okay, we know that a gain and phase shift, okay, these are the two things which are dependent on frequency. Okay, similarly you'll remember a beta. Okay, a beta, it's a complex number. Okay, it's a complex number and it is dependent on the frequency. We had seen this in our previous videos also. Now when I say it is dependent on frequency, what I'll do is that now I'll keep on changing the frequency. because I know that the gain doesn't remain the same for all frequencies, right? For lower frequency, higher frequency, it is less. Only for the mid frequency, it is constant, right? So I'll keep on changing the frequency and I'll note down all the values of A beta, A into beta at that point of time. See, suppose at 10 Hertz, I note down the value for A beta. Similarly, at 20 Hertz, I note down the value of A beta and so on. Okay, for various values of frequency, I make a table of A beta. So after checking out for all the frequencies, what I'll do is that I'll plot this onto a graph, okay? And when I plot onto the graph, I will join all the points which will form a closed curve, okay? Locus of all these points will form a closed curve, okay? So once the curve is formed, that time I can define my Nyquist criterion, okay? What does Nyquist criteria state? It states that amplifier is unstable if Nyquist curve encloses -1 plus j0 point. This is a very important point, -1 plus j0 point. You will come to know later as in when we progress with this particular video. So as of now, you'll just remember this -1 plus j0. It is nothing but -1, okay? Just to represent in the complex plane, I have to write this plus j0. Understood? So it is unstable if at all it encloses this point. And if at all it doesn't enclose, it is stable. Amplifier I will call it to be stable. Fine. We'll just have a look over here what we just discussed. Okay. This is that locus of all the points, A beta terms. Okay. After joining all the points, if at all this curve is not taking into consideration this -1, then the system is stable. If at all it is enclosing that point, this -1 point is lying within this curve, right? So this system will be unstable. Okay, stable and unstable. Fine. Now, this is very general that I am talking about with respect to amplifier. But I know that, in feedback amplifiers, there can be positive feedback as well as negative feedback. So for this also, Nyquist criteria do help me to decide on the stability. Let's have a look at this particular diagram or the graph. Okay, again it's a complex plane and I have a locus of 1 plus A beta equal to 1. This circle represents 1 plus A beta, okay, equals 1 with center as -1 plus j0, okay. Say suppose 1 plus A beta is greater than 1. If at all it is greater than 1, I will say that the feedback is negative. Why? Outside this unity circle it is all negative, okay, you can see over here. And inside this unity circle it is all positive feedback. If at all 1 plus A beta is less than 1, then I will call it to be positive feedback, okay, because it's lying within this, right? A beta will lie within the unity circle when 1 plus A beta is less than 1. So that time I will say that feedback is positive, okay. Now, continuing with the another parameters with respect to the stability, that is gain margin and phase margin, okay. Now, gain margin and phase margin, let me be very clear to you all. First of all, these are the two parameters which can be varied. You can vary it, but don't vary it in such a way that your system becomes unstable, okay. So these are variable parameters. So there should be some margin, right, wherein I come to know that I should not vary it too much. So this is decided by gain margin and phase margin, okay. We do this on board plots, okay. There is something known as board plots which you are going to study in SEM 5 in detail in control system engineering. Now what do we do over here is that first of all gain margin and phase margin goes hand in hand, meaning only one alone you cannot find it out, you have to find both together, okay. So two graphs are required, that is gain versus frequency and phase versus frequency, okay. Here you can see there is a curve for gain, here there is a curve for phase, okay. Now let me consider first thing, that is gain margin. To find gain margin, I require something known as phase crossover frequency, okay. I told you all both goes hand in hand. So from one curve I am going to determine other, fine. So to find gain margin, I will require phase crossover frequency. Now what is phase crossover frequency? It is the frequency at which the phase has crossed 180 degrees, okay. So at 180 degrees it is coinciding, right, with this curve. So this point is your phase crossover frequency. What am I supposed to do with this particular frequency? I am supposed to produce this frequency onto the gain curve. Okay. Now, it is coinciding with this gain curve, right? So I got one particular point over here. Okay. And the gain margin is the difference from 0 dB to that point, which we have found due to phase crossover frequency. Okay. So if at all I find out gain margin, this point is negative, right? See, it is below 0, so it is negative. So it is 0 minus of minus this particular value. Let us consider minus 20. So 0 minus of minus 20 is 20 dB. So gain margin is positive, which is 20 dB. Fine. Similarly, I can find out phase margin. How to find out phase margin? To find out phase margin, I will require something known as gain crossover frequency. Just like to find out gain margin, I required phase crossover frequency. I will require gain crossover frequency to find out phase margin. What is gain crossover frequency? It is the frequency at which the gain curve crosses 0 dB. Okay, so it is this point, right? Okay, so I am supposed to produce this point over here on to the phase curve. Okay, and it is coinciding over here. Then the difference between these two, 180 degree and this point, will give me phase margin. Okay, I hope this is clear to you all. So how does it decide on the stability? If at all gain margin is positive, I would say that the amplifier is stable. Okay, if it is negative, then the amplifier is unstable. Similarly, it goes with phase margin also. Okay, I hope this is clear to you all. Okay, this is what I was just telling you all, stable system and unstable system. If I get positive gain margin, positive phase margin, I say the system is stable. Okay, now when I say positive gain margin, please have a look over here. This is the point, it is lying below 0 line, right? How do we measure gain margin? It is with respect to 0, so it is 0 minus of minus, this is minus value. Why? Because it is below 0. Okay, so minus of say 20 dB, so 0 minus of minus 20 dB will give me plus 20 dB, which is positive. So I can say that the system is stable. Similarly over here, okay, I will consider this magnitude, okay. So 180 degree minus this particular value, okay, which will give me something less. I mean, it will give me something positive. So it is positive phase margin. Okay, similarly over here, let me consider this point to be 20 dB. So it is 0 minus 20 dB, which will be minus 20 dB. So definitely my gain margin is negative here. So I will say that the system is unstable. Similarly over here, I have 180 degree. 180 degree minus, this will be larger value than 180 degree. Remember, we are taking magnitude. So 180 degree minus this greater value, which will give me negative again. Okay, so I hope this is clear to you all with respect to stable and unstable systems. Now we will start with oscillators. Okay, all the prerequisites are done with respect to the stability. Now we will start with oscillator. What is oscillator? First of all, oscillator is the one which produces alternating current, which means an AC signal. Okay, so it produces a sinusoid, okay, with known frequency and amplitude. Okay, now oscillator generates sinusoid, it doesn't create energy. Okay, it converts energy. Okay, let me be very clear with this. What it converts? It converts DC energy into AC current, okay, of desired frequency. Exactly opposite to that of rectifiers. What rectifiers used to do? It used to convert your AC to pulsating DC, if you all remember, right? So similarly, oscillator is exactly opposite. It converts DC into AC. Fine. Let us have a look at the differences between amplifier and oscillator. Amplifier is something which strengthens the signal, okay, which doesn't change any frequency or something of that sort. Okay, but oscillator, it converts the DC current into AC current of desired frequency. Okay, whichever is the frequency at which we have designed the circuit. Okay, now amplifier, you all remember, an amplifier, while doing the experiment, we used to provide input AC signal of 20 millivolts or 50 millivolts something, and we used to get the output. Okay, also there was VCC, which was like 12 volts or 9 volts something. Okay, so there are two things which are coming into picture. So additional power I can consider it to be a DC source over here. Okay, but in oscillators you don't require any additional power. It produces oscillations by itself. Okay, it maintains the process of energy conversion that we are going to see in the later part of the video. Then here energy conversion process is controlled by input signal, that is AC signal again. Here energy conversion is controlled by oscillator circuit itself. Fine. To summarize both the things, you can just have a look over here. I have an input signal DC power which produces output signal. This is my amplifier. Wherein in oscillator, just with DC power input, it will produce the AC signal. Okay, I hope this is clear to you all. Next is classification of oscillators. Now oscillators are classified into many categories. First we'll see with respect to the function, like how we have it in our lab, the function generator, signal generator, and there is something known as standard signal generator also. Then based on the fundamental mechanism, I have negative resistance oscillator and feedback oscillators. Feedback oscillators are the ones which are commonly used. Negative resistance oscillators are the ones which makes use of the principle of negative resistance. For example, I can consider tunnel diodes. Okay, if at all I look at the VI characteristics of tunnel diode, which we have studied in EDC 1 also, it has something known as negative resistance curve. Okay, so it makes use of that principle. Okay, that is negative resistance. So those oscillators are named as negative resistance oscillators. Then based on the frequencies which are generated, say suppose I want to generate a frequency of say 300 megahertz, okay, or 320 megahertz to be somewhere in between. So I will have ultra high frequency oscillators. So depending upon the frequency which you want, there are different types of oscillators. Okay, and finally depending upon the type of circuit, that is which components are used, whether inductor and capacitor are used. If at all L and C are used, I'll name it as LC oscillator. If R and C are used, I'll name it as RC oscillators. Now oscillators can be broadly classified into two categories, that is harmonic oscillators and relaxation oscillators. Harmonic oscillators are the ones which will allow the flow of energy in one direction only. Now which direction? It is from active components to passive components. Which are the active components? Like BJT, JFET, and maybe you can consider op-amp also. Yeah. Which are the passive components? Passive components are R, L and C. Okay. Similarly for relaxation oscillator, there is exchange of energy that takes place between the components, active components and passive components. Okay, so this is a major difference between the two. Then the frequency of oscillation is determined by your feedback path. Here the frequencies of oscillation in case of relaxation oscillator, it is determined by the time constant because of charging and discharging, okay, of the components. Okay, during the energy transfer, the frequency of oscillation is determined by charging and discharging of time constants. And harmonic oscillators are the ones who generate the signals with low distortion and a sinusoidal output. Here it produces non-sinusoidal outputs, like for example you have sawtooth waveform, square and triangular. Okay, these are some examples. Now coming to the major part of this particular video, that is Barkhausen's criterion. Okay, without this you won't understand how oscillator operates, so please listen to this carefully. To understand this Barkhausen's criterion, we'll consider an inverting amplifier. In inverting amplifier, you all know that when I give the input signal, it will produce the output signal which is out of phase with respect to input, right? So it produces 180 degree out of phase. Okay, but you know that in oscillators this VI won't exist. Okay, in oscillators I cannot give this VI. Fine. So for that, what I need to do is, for oscillators I will have a feedback network over here, right? Okay, and this feedback network should be able to produce this Vi. Okay. Now, Vi and Vout both are out of phase. So what should feedback network do over here? This will be the input to the feedback network, right? So feedback network cannot give this only as the input to the amplifier, because input to the amplifier should be in phase. That time only it will result in positive feedback. You'll remember in the feedback concept video we had discussed this. Okay, so it should be the same. Let's have a look at this diagram. You'll understand it better. You have a basic amplifier. Vi doesn't exist, as I told you all. Okay, you get the output which is inverting because it's an inverting amplifier. Okay, this inverting input is given over here. Feedback network cannot give this input only directly over here. The reason being that to result positive feedback, what should happen? Both the inputs should be in phase. Okay, and that is the reason feedback network is supposed to introduce some phase shift. Okay, so it will invert this particular input and then give it over here. Fine. So to understand the working of this oscillator circuit, we'll consider input which is not existing. Basically, those inputs we call fictitious input. Okay, Vi. So Vi, we consider an input which is applied over here. Okay, so what will be the output? It will be A times input. So V0 is equal to A Vi. Okay, let me call it equation 1. Okay, now please go with the flow as of now. Okay, later on you will understand things. Even though the input is not existing, why I have considered it. Fine. Okay, now let us come to the feedback network. Okay, for that input is V0, output is beta V0 or Vf. Okay, so but this feedback network is little unique because it will introduce another phase shift. So what I will have to do is that I cannot write Vf is equal to beta V0. I'll have to write Vf is equal to minus beta V0, because it introduces another extra phase shift. Okay, so to make the difference between the two, I will have to consider this as minus beta V0. Okay, let me call this equation 2. Now substitute this equation 1 over here. So what will it be? Vf is equal to minus beta AVI. Okay, so you have minus A beta Vi. Okay, but what I had told you all, Vi doesn't exist. Feedback network should generate Vi. Okay, which means Vf should be equal to Vi. Correct? So I'll use that condition now next, because I know that in oscillators Vi doesn't exist. So Vf should act like Vi. So I'll substitute in this particular equation Vf as Vi. Okay, so you can see over here Vi on both the sides. Okay, now this will get satisfied only when this condition gets satisfied, that is minus A beta is equal to 1. This Vi will get cancelled on both the sides. So you'll get minus A beta is equal to 1. And this condition is known as Barkhausen's criteria. Okay, so I have minus A beta is equal to 1. Okay, so I can write this minus A beta is equal to 1 as A beta is equal to minus 1. Okay, plus J0. Okay, now you'll remember why this minus 1 plus J0 is important. I had explained this same thing in Nyquist criterion also. Okay, this minus 1 plus J0 significance. Fine. I hope this is clear to you all. Barkhausen's criteria. Now I'll take that Barkhausen's criteria, and what I'll do is that I'll apply magnitude on both the sides. So what I'll get, magnitude of A beta is equal to minus 1 plus J0 magnitude, which is going to be magnitude of A beta is equal to 1. Okay, now let's have a look at this diagram again. Just to summarize, one condition of Barkhausen's criteria is that magnitude of A beta should be 1. Second condition is over here. Okay, and what is that? See, we know that this amplifier is introducing 180-degree phase shift. Correct? This feedback network is also introducing another phase shift. So what is the total phase shift in this particular loop? it is 180 and another 180, which is 360 degree, which means for sustained oscillations, that two things should be satisfied. First of all, magnitude of A beta should be 1. Second, the total phase shift in the loop should be 360 degree, which is equal to 0 degree. Okay. So these are the things which we need to note down over here. So Barkhausen criterion states that total phase shift around a loop should be 360 degree or 0 degree. And second thing, magnitude of product of open loop gain and feedback factor should be unity. Okay, I hope this is clear to you all what is Barkhausen's criteria. This is a very important thing and this should exist in oscillator circuit. But in reality, we know that no input is needed to start the oscillation. So what is done practically is that initially, directly we don't consider A beta is equal to 1. We will start only, we'll set up A beta as greater than 1. We know A and beta, these are known parameters to us. So A and beta is set greater than 1 to start the oscillations initially. And then later on circuit will try to adjust itself and set A beta is equal to 1 in order to achieve the sustained oscillation. Okay. Now we'll see what happens if A beta is not 1, meaning if it is greater than 1, if it is less than 1. Okay. Imagine that we have maintained the phase shift of 360 degree and A beta we have set it greater than 1. That time what happens is that we get the oscillations nicely, okay, but those are growing oscillations. Now what do you mean by growing oscillations? They are increasing, okay. Such oscillations are not sustained oscillation, they are not with constant amplitude and frequency, it's changing, okay. So this happens when A beta is greater than 1. When A beta is equal to 1, it results in sustained oscillations. You all can see over here, they are of constant amplitude and constant frequency. And when A beta is less than 1, what happens is that initially nicely it generates the oscillations, but later on they try to decrease. Amplitude goes on decreasing and eventually they die off. Okay? So this is what happens. So what should happen is that we need to take into consideration 360 degree phase shift, okay, overall phase shift, and we also need to take into consideration the phase shift and the loop gain, okay. With respect to the loop gain, that is magnitude of A beta should be equal to 1, okay. So these things we need to take care so that we get sustained oscillations. We have spoken about sustained oscillation now, but from where do the oscillator gets the starting voltage? Okay, initially there is nothing to generate the feedback signal or to get the amplifier output. From where is the oscillator getting the starting input? Okay, that we are going to see now. Okay, if no input is required, how oscillator starts and from where does the starting voltage come from? Fine. These two things we are going to attack now, these two conditions. So to understand, we know that in the oscillator circuit itself, there is amplifier, right? And in amplifier, there are some resistors, okay? Now since there are some resistors, we know that, resistors have some electrons, okay? So resistors, imagine a resistors now. Now this is a resistor which has atom and some electrons around. There are some electrons. Okay, and at room temperature, what happens to these electrons? These electrons are free electrons, they start moving. Okay, and since this electron starts moving, what happens is that it results in some voltage. Movement of electrons meaning the electrons are moving in the sense some voltage is generated, right? Okay, so it will generate some voltage and that voltage, let me name it as noise voltage. Okay, so it generates noise voltage. So what is done is that when DC supply is applied to the amplifier, this noise voltage I wanted to get amplified, okay, and that's how you get the initial output in the amplifier circuit. Fine. So it will start generating. Because of this noise voltage, what happens is that it will produce the output, amplifier is going to produce the output, and we try to maintain A beta greater than 1 initially so that this noise voltage gets amplified. Fine. And later on the amplifier will try to, or the network is going to try to adjust itself to maintain this A beta is equal to 1 along with this phase shift to get sustained oscillation. To understand more in detail, let's have a look over here. This is the amplifier which I was talking about. There are some resistors inside. So resistors will have free electrons inside that. So since it has free electrons inside that, at room temperature it will start moving, right? And since it starts moving, what it will do is that it will try to generate some voltage, and that voltage is named as noise voltage, and because of which I'll get some output over here. This output is fed back over here, okay, which is given back to this oscillatory circuit, okay, and that is how now things will go on and on. Okay, I hope this concept is clear to you all from where oscillator gets the starting voltage. Fine. Let us understand this now summarized block diagram from all the concepts we have studied. So first you have oscillator circuit, which can be LC, RC or crystal depending upon what frequencies and all you want. Second thing, amplifier. Okay, you have DC power which is getting converted to AC over here. Okay, now there are some losses that happens while this input which is being fed to this oscillatory circuit, which we are going to discuss later, okay, about the losses. And you all know about the positive feedback network. It gives the part of output back to the input to ensure the positive feedback. So this is the summarized block diagram of oscillator circuit. Now we will study little bit about LC oscillators. I had told you all, depending upon the circuit, there are two types of oscillators, LC oscillators and RC oscillators. Okay, so LC oscillators, as the name suggests, L and C components are used. Okay, they are also known as tank circuit. Together they are known as tank circuit, oscillatory circuit, resonant circuit or tuned circuit. These are 4 different names, so please don't get confused. These oscillators can generate high frequencies. Okay, and there are various types of LC oscillators which are listed over here, which we are going to study. Fine. To understand LC oscillators, first of all we need to understand how LC, that is inductor and capacitor, together they form a tank circuit. So how they both operate together, that we need to understand first. Okay, that we will try to understand now. So when I say LC, L and C are connected in parallel. Okay, to understand the working, let us consider that the capacitor is connected to a DC source and it has got initially charged. Okay, in this manner, wherein there is all positive and all negative over here. Okay, now what happens is that since this capacitor is connected, it's charged initially, I will connect now inductor in parallel to this particular capacitor. Okay, and the capacitor is fully charged. So what it will do now? It will discharge via this inductor. Okay, and when the capacitor discharge, current starts flowing from positive side to the negative side. So it will, what will happen over here is that this inductor is going to store the energy now. What was the energy stored in the capacitor? It was electrostatic energy. Okay, capacitor always stores the energy in the form of electrostatic energy. So this energy is being given to the inductor, and inductor stores the energy in the form of magnetic energy. Okay, so it will store the energy in the form of magnetic energy. So entire electrostatic energy from the capacitor is being converted into magnetic energy in the inductor. Okay, now when inductor has got the entire magnetic energy, or it has stored the entire energy, what it will do now is it will unleash the energy back into the capacitor. Okay, so while doing this, what it does is it does it in the opposite direction, and we call it as counter EMF, electromotive force. Okay, So it sets up the current in the opposite direction, as you all can see over here in this particular direction. And since it sets up the current in the opposite direction, the capacitor gets charged now, but in the opposite direction. Okay, previously you all had seen that there were negative charges over here, and here there were positive charges. Now here there are positive and here there are negative. So it is getting charged in the opposite direction now. Okay, meanwhile the inductor is unleashing its energy. Capacitor is getting charged. Okay, and this is basically counter EMF is set up only because of Lenz's law, if you all remember. Okay, basic principle of inductor. Okay, now when inductor is unleashing its energy, capacitor is now charged fully but in the opposite direction. Okay, so again entire magnetic energy has got converted back into electrostatic energy. Okay, again the same things will repeat. Capacitor, once it is fully charged, it will discharge. Okay, it will give the current in this particular direction, and inductor is going to store the energy in magnetic energy form. Okay, same things are going to repeat. Again the energy is going to get converted from electrostatic energy to magnetic energy, and so on. So what do we notice from this is the capacitor which was initially charged was in the opposite direction, and now it has got charged in a different direction, which means the current which was set up in the circuit is nothing but the oscillatory current. Okay, it is termed as oscillatory current or alternating current. Now, what are the results of this LC tank circuit? See, every time the energy was getting transferred, right, from capacitor to inductor, inductor to capacitor. So what has happened is that losses occur due to this. Okay, these are the losses which I had told you all that I will be explaining later in the generalized block diagram. Okay, so the losses occur when the energy gets transferred from C to L or L to C. These losses, okay, because of these losses, what happens is that the current reduces. Okay, as the time progresses, the current reduces, and these oscillations will eventually die off. Okay, so from this we come to know that LC tank circuit alone cannot generate sustained oscillations. It requires some additional circuit, and that additional circuit is known as the amplifier. Okay, transistor will supply the loss of energy at proper times. Okay, so we have seen this. So transistor is the one who is going to supply the energy at the proper times, and it will result in sustained oscillations, and the frequency of oscillation by LC tank circuit is given as F is equal to 1 upon 2 pi root LC. This is the final equation for this. I'll stop over here. These are my references. I refer to textbooks, and these are for images basically. Thank you.